Okay, I think we're recording. Suji. It's Eric. Morning. So if I think Padraig is still not here, so if when he comes in, let me know, because I'm gonna share my screen and go to this one. It is a real problem that Zoom only doesn't let you really, when Zoom says you can share a screen, it doesn't mean it's lying. There we go. Because it only lets you share a window. It doesn't let you share a screen. And I'd really like to be able to put two windows on the same screen and have that shared, but that's not what we're living with today. So here's more or less where we stopped. I went, I had skipped a little stuff, so I want to go back and pick that up, some more information about surface tension, and I'm going to do that with the DocuCam. So hopefully everybody can see my pad and my pen. Say something if you can't. So we want to talk about surface energy. And one way to define surface energy, so I gave you the thermodynamic formula, but one way to think about it, one way to define it, is if you have say you have a rectangular solid, and I'm not much of an artist, so bear with me here. And then you take it through an operation where basically you just cut it, right? So if this is a unit area, right? And the length doesn't matter, any kind of length. But if this is a unit area, and then you cut it in two, what have you done? Suji, what's the net result here?
Yes, sir.
You can see this, right? You can see what my drawing on the pad.
Yeah. So
what happens here?
What do you mean by like what happens? What happens in terms of what? In terms of surface energy?
Yeah. What's the difference here?
Oh, you will now create two surfaces, so you
That's
will
correct.
need some form of energy to like create those surfaces, right?
That's correct. Very good. So you have, if this is a unit area, then you have two unit areas of surface here, right? And surface energy is almost always given the symbol gamma. And because we created two, what's happened here is you've created two gamma, right? So now another way to think about surface energy, and I think we can do, I think I can do this on the slides. I think I have a slide for this. Okay, so right, so now consider the situation where we have a drop of water. So it's going to start out as teardrop shape, or we can also, just for ease of thinking about it, consider it a sphere. The sphere or the teardrop is going to hit the surface. And what's going to happen? It's going to spread out, right? So it's going to spread out, and when it stops spreading, and depending on the liquid that you have, whether it's water or something else, and the surface, there's going to be either, it will have some kind of a contact angle. So this is the definition of contact angle. You assume that it's symmetrical, so you can draw it from this side also, and it should be the same thing. This doesn't look quite symmetrical to me, but that's because of my lack of skill at being an artist. So you take the tangent to the drop at the surface and draw a line. And the angle here, almost always called theta, is the contact angle. So, and I know that when you get down to molecular dimensions, the trying to draw the tangent gets a little crazy. So this is this is kind of I would call it kind of semi-quantitative, but people use it all the time and they call it quantitative. So trying to figure out where that tangent line in, I think, is a little bit subjective, but people do it all the time. It's a standard way to measure stuff, okay? And and then from this situation, we can derive an equation called Young's equation. So Young's equation is, it relates the contact angle to the surface energy. So the reason it's so important is measuring contact angle is one way to measure the surface energy. Now, you can derive Young's equation from first principles. It has been done. I tried to do it. I went to the mathematics department to get some help with the math, and it was 2 pages of really complicated math to do it from first principles. But it can be done. We're not going to go over that here. And excuse me. So so I'm going to do it a different way. So we're going to do an incorrect derivation, but it gives you the right answer, and conceptually it's much easier to understand. So okay, so what we do is what we do is we say, okay, now the drop lands on the surface and it spreads out, and the question is, how far does it spread? Well, there are forces involved, and we can use vectors to describe those forces. So there is a force between the liquid, so this is the liquid, right, and the vapor, which is air, so we call it LV. So this contact angle gives you a force according to the tangent of the liquid, that is gamma LV. There's another force between the drop and the surface. So this vector is what pulls the drop and spreads things out, right? So it's going to spread the drop. And then there's a third vector that goes in the opposite direction. So this is solid. This is S down here, solid and liquid. And this is solid and vapor, right? Okay, so we have these 3 vectors. And then what we can say is the drop will stop spreading. Sum of the forces is equal to 0. There's no force, there's no movement, right? So we just simply write these out. So you have plus gamma SV minus gamma SL minus LV times the cosine of theta, because the vector, all we're concerned about here is the spreading of the drop. And that happens at the interface between the air, the drop, and the solid or the substrate. So all we're interested in is the forces right at this joint. And so the force going in, and we're interested in whether or not it spreads. So we're interested in forces going to the right, forces going to the left. Well, the force from gamma LV that's going to the left is gamma LV cosine theta, right? So you could draw a little triangle here, right? So that's gamma LV cosine theta. And then that gives rise to, you just rearrange it simply, and you get rid of the minuses, and you get gamma SV equals gamma SL plus gamma LV cosine theta. That is Young's equation. I think it's the same Young that does Young's modulus. So that's Young's equation, and that's a derivation that is easy to follow, but it's not correct. The reason it's not correct is these are not forces, these are energies, these are surface energies. So that's the difference, but it's a good way to visualize it, okay? Let's see. So then we also have, besides surface energy, we also have cohesion, and cohesion is defined here. We've talked about it before. If you didn't have cohesive forces within a liquid, then you would have, never have a liquid, you'd have a gas. So there must be some kind of forces, even van der Waals forces at a minimum. You always have those, right? And that will give you a, what's this? Annabelle's having trouble with her computer, I think. So, so if you have a liquid or a solid, you're going to have cohesive forces, right? And whether those cohesive forces are simply energies or they're forces, right? But they come from an energy of holding the attraction between the atoms and the molecules involved in the liquid, the solid, or the gas. And as I've mentioned before, and it's part of your homework problem, the substance will turn from a liquid to a gas when the energy, the thermal energy, KT for molecules, RT for by the mole or moles of substances. When the thermal energy exceeds the cohesive forces, I have a boiling point. And you also have a melting point when the thermal energy, KT or RT, exceeds the cohesive forces holding the solid together, and then it becomes a liquid. Okay. So this term cohesion is going to come up again. Right? And, well, it's going to come up right now because I'm going to do this. That's not what I wanted to do. There. Okay. So if we have two pieces of wood that are glued together and we pull them apart, an internal bond experiment, there's three different things that can happen. So you have two pieces of wood and you pull them apart and you look at the fracture surfaces. So you have a situation, and what you're going to end up with is a situation like this. Okay. So if the wood is white, or the color of the pad, and the adhesive is black, then what you've got here is different kinds of failure. So here you have cohesive failure of the adherents. Okay. And in this case, you have adhesive failure. So do you see that? So here you have cohesive failure of the adherent or the wood, because when you break it, all you see is wood. All you see is white, right? The wood is white. So all you see is wood. You have cohesive failure of the adherent. If you have one piece is white, one side is white, and one side is black, then that means it broke between the adhesive and the wood. So that's adhesive failure. But you can also have cohesive failure of the adhesive. So if you adhesive for some reason isn't working, and you take two pieces and you do an internal bond test, you pull them apart, and you open up and look at the fracture surfaces, if you see adhesive on both sides, you call that cohesive failure of the adhesive. So 3 different scenarios there. Okay. Back here. Oh, there we go. Share screen. Here. All right. Okay, that takes us through surface energy. So now let's talk about polymers and why they're used as glue. So I've said this before, polymer means many, mer means parts, so polymer means many parts. And you make a polymer like this. So you have say you have a compound, a molecule, and we're going to just call it just schematically AB, right? With AB. And this is called the monomer, not the polymer, monomer. So it's one part, right? But it reacts, A reacts with B under certain conditions. So we put it in those conditions, and so we get AB, AB, right? And then it can under, if the conditions are right, if we're doing our job correctly, it can react again. So you get another AB that reacts, so you get AB, AB, AB. And in the general case, we can write this as a chemical reaction. We say NABs goes to ABN. And this is how you write the chemical formula for a polymer. Now, generally, if N is less than 100, you call it an oligomer, not a polymer, but there are exceptions to that. But that's just kind of and that's a rule of thumb. It's not like written in stone anywhere. So that gives you some idea, though, of how big polymers can be. And actually, N can go to thousands. And the molecular weight, for example, of a commercial PET water bottle is, I'm not sure, somewhere in the neighborhood of 100 to 200,000. Polystyrene, commercial high-density polyethylene, which is milk jugs, molecular weight there is close to 300,000, 200,000 to 300,000. And of course, DNA can be millions, right? And ultra high density molecular weight polyethylene can also be up in the millions. Enzymes are also polymers. Their molecular weight is not that high, but it can easily be 50,000. Okay. And so for polyethylene, here's my model. So the yellow balls here are hydrogens and the black are carbon, because that's the formula for polyethylene. Ethylene is CH2 double bond CH2. And you make polyethylene by taking the double bond and flipping it to the next ethylene. So this originally starts with a double bond. I'm trying to get this on the screen. So you can originally, this starts with a double bond. Within that double bond will flip, and it will flip to the next ethylene and click, 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 make a polymer. So polyethylene is the simplest polymer, and it's the one you'll see in all the textbooks, and it's the one that people use as an example. And it's had, I don't know, thousands and thousands and thousands of journal articles written about it. Okay. All right, so that's what a polymer is. Tiana, are you comfortable with that?
Yes, it
Okay.
reminded me of the papers I read.
Okay. All right, good. So recycling is kind of different these days, but we still have the recycling code. And so you have, here's a abbreviation, the polymer, and a typical use for it. There's many uses for PET. It's very versatile. Soda bottles or water bottles is a good one. And then milk jugs for high density polyethylene. You also have low density polyethylene, which are grocery bags, right? Yeah, they're a blend. Actually, a grocery bag has, now I forget how many. It has a number of different layers. Even though it's really thin, it has a bunch of different layers. And PVC, most people are familiar with that because it's plumbing pipe. Also, rubber duckies are usually made out of PVC. And if you have vinyl siding on a house, it's also PVC. Then polypropylene, usually when you have a PET bottle, it usually has a polypropylene cap on it. That's why when you recycle the bottle and you throw the cap away, because they're two different polymers. So, and you can, well, recycling technology is a whole nother course, right? And there's not that much being done today, and I think it's less than 5% of polymers are recycled. Most of them end up in the landfill or as unsightly litter or in the ocean gyre. So, and polystyrene is styrofoam cups, right? Or any kind of styrofoam. And then there are thousands of things that are number 7, which is other, not really recyclable. Okay. Cellulose, lignin, and hemicellulose are all polymers, right? So when we're talking about wood, we're talking about polymers. And then you have things like proteins or enzymes, DNA, RNA, not so much petroleum and natural, well, petroleum is a huge mixture of all kinds of stuff, but including some polymers, but mostly just high molecular weight and low molecular weight molecules. But there are some polymers in there, and most polymers are made from petroleum, right? Then there's natural rubber. So natural rubber is also a polymer. These first 3, proteins, DNA, and RNA, I prefer to call them macromolecules. And the reason for that is because they don't repeat, right? So enzymes, DNA, and RNA all have a specific sequence. So some people will call them polymers, but I think it's better to call them macromolecules because they don't have a repeat unit. They have a code, yeah? And so you have a specific sequence of, you still have a certain number of monomers like DNA. You've got 4 bases, right, to make DNA, things like that. So you have proteins, you've got 20 amino acids that the proteins are made out of, but they don't have a repeat unit. So let's call them macromolecules. And other types of synthetic polymers are polyurethane, abbreviated PUR, foam cushions, et cetera. PMDI is not, it says polyurethane, and there's some polyurethane in it, but it's not really polyurethane, it's polyurea. So I need to change this. So this is polyurea, and that's what isocyanate adhesives are made out of. We're going to cover that. Then phenol formaldehyde, urea formaldehyde. These 3 are the big 3 in glued wood composites that are made on a large scale. Right? Furniture is different. Furniture usually uses a different adhesive. And then your car rides on SBR, styrene butadiene rubber. Right? Sometimes there's natural rubber in tires also, but most of it is SBR. Rubber bands can be natural rubber or SBR. So there's some definitions. There's a definitions of 2 words here. This is more lingo to memorize. A thermoplastic can be melted and reformed. A thermoset cannot be melted and reformed. So I like to think of them this way: is thermoplastics melt before they burn, thermosets burn before. And there's a reason for that. So the reason is a thermoplastic. So if this is the polymer chain, right? So there's 3 polymer chains here, and they're not connected. So there's secondary forces. There's van der Waals forces. There may be hydrogen bonds, etc., but they're not covalently bonded. If you go through an operation or a chemical reaction where you start putting chemical bonds between these polymer chains, then all of a sudden they're all connected and they have to move all together. If you have these individual chains, when you get the temperature high enough to exceed the energy of the secondary forces holding them together, then they can slide past each other, and we call that molten or melted, right? So these can melt, and then when you stop, you lower the temperature, the secondary forces come into play now, and it becomes a solid again. So that's thermoplastic. But when you have thermoset, when you have crosslinks here, then that can't happen. You raise the temperature, you have to raise the temperature enough to degrade the entire polymer and break the covalent bonds in order for these things to slide. Well, actually, we don't call that sliding, we call it degradation, right? So the thermosets burn before they melt. And and this picture makes it look like that this thing is night and day, black and white, but that's not the case. So depending on the degree of cross-linking, how many cross-links you have per unit weight or per mole of the polymer, you can get various properties. So it's a continuous spectrum between thermoplastic and thermoset. It's not black and white, but we still use these 2 terms. And the major wood preservatives, phenol formaldehyde, urea formaldehyde, and isocyanates are all thermosets, right? Okay. Now, polymers also have various kinds of mechanical properties, and there's these 4 different kinds, right? So you can have viscous, you can have viscoelastic, elastic plastic, and most of them are elastic plastic. So when you stretch them, they will rebound a little bit. And let me stop sharing here. So the way I like to think about this is, if you have an elastic material, if you grab on either end and you pull it and let go, it snaps back to where it started. If you have the elastic plastic, which is what most polymers are, you pull on it both ends. I got to stay on screen. You pull on both ends and let go, it goes part way back. If it's viscous, you grab both ends, you pull, you let go, it stays where it's at, right? So one example of that is silly putty. Anybody not play with silly putty when you were kids? So silly putty is elastic plastic, but it also demonstrates another property of elastic plastic or materials that have some viscoelastic or elastic plastic, some kind of plastic property. If you pull it slowly, right, it doesn't break. But now let me put it back together. Get a grip. But if you pull it fast, it breaks. So what's going on there is the polymers are very large molecules, right? They're very large, and they have, and when you pull on them, it's like pulling on, well, I could say snakes, or it's like just like pulling on a long string, right? If you have a ball of strings and you start pulling on one of the strings, it takes a little time for things to unwind, right? So when you're pulling if you're trying to pull one string out of a ball of strings, then if you go really slow, it has time to slide past the other ones that come out. If you try and pull it fast, the whole ball of string comes up. So it's the same idea here. It's called relaxation time. So if you're moving faster than the relaxation time of the polymer, then then it will break. And if you're moving slower than the relaxation time of the polymer, it has time to relax, it has time to move. The polymers have time to slide past each other, and then it stretches. Right? So another example of that, and for this I need to, I don't know if you're going to be able to see this. You can unmute and let me know. Okay. So I have two balls here, right? And you're sitting in the back of the room, I think. So this is an elastic ball, right? So it's bouncing. It's my happy ball. And it's not bouncing back 100%, but some of the energy, I mean, the substrate here, the table, is also a bit on the not perfectly elastic, right? So that's my happy ball. It can bounce all day. This is my sad ball. This is viscous, right? So you can see the difference between viscous material and an elastic material. Hopefully you saw that, and hopefully it made sense to you. So, okay, back to the PowerPoint. So we have these different kinds of mechanical properties that can take place. All right, so now I have to go back to the we're not ready for this, so I need to go back to the stop the share. Oh man, this really breaks my rhythm. Okay. Usually write this on the board, but I'm going to write it on my pad now. So to make a good adhesive, we need a trick, because back to fundamentals. If you're going to get a good adhesive bond, then you need to have forces, right? adhesion resists separation. So you have to have forces that hold things together. We know that van der Waals forces and hydrogen bonding and mechanical interlocking are the three major forces for most adhesives, not all, but most adhesives, right? Especially the ones that glue wood together. So, and the adhesion theory is the most important one. The van der Waals are the most important. If you don't have that, you don't have squat. You're not going to get a good adhesive bond. But we also know that the only way that you get good van der Waals forces is to have intimate contact. They have to be really close, less than a nanometer, usually less than half a nanometer. That's really close, right? Or we could do it in angstroms, right? And a nanometer is 10 angstroms. So you have, to get good van der Waals bonding, you need to be less than 5 angstroms. A carbon-carbon bond, or a carbon atom itself, is 1 angstrom. So you have to be just a few atoms apart before the van der Waals forces really get strong enough to make a difference. So you have to have this intimate bonding. Well, how are you going to get that? If you just put two solids together, they're going to have some kind of surface roughness that's more than a few atoms, right? So you're not going to get the van der Waals forces if you just put two solids together, unless you're a gecko and you've got a foot like that, right? So the way it's done with wood adhesives is you apply the glue as a liquid. The liquid then can spread out on the surface, and the liquid will be in close contact with the surface. It will even absorb it, right? It will sink in for you want it to sink in for a few wood cells, usually around 3 to 5. And so then you have lots of surface area, and you pick up the van der Waals forces and the hydrogen bonding in the case of wood. So all of the three major wood adhesives also have plenty of hydrogen bonding going on. So that's how we get a good adhesive bond. But if we take our polymer and we put it on as a liquid, we need to turn it into a solid. Otherwise, if it's just a liquid, you just pull it apart. And in fact, if you have sticky notes or Post-it notes, then that's actually what's going on. You have a polymer that's sticky, but it's still somewhat liquid. So it's kind of in between, right? So you don't cure it. You don't put it on as a liquid, then cure it into a solid and get a really strong adhesive bond. You kind of have it in between. You put it on, it's enough of a liquid that you get intimate contact, but it's not enough of a solid that you get a really strong resistance to separation, because that's what adhesion is all about. So then you can peel it right off, right? So what we want to get a good adhesive bond for wood composites, CLT, glulam beams, plywood, MDF, particle board, what we want is to put it on as a liquid so we get van der Waals forces, hydrogen bonding, and then turn it into a solid so that when we pull on it, we get cohesive failure of the adherent, cohesive failure of the wood. If the adhesive and the bond between the wood and the adhesive is stronger than the wood itself, we're done, right? It doesn't matter how much stronger you make it than that, the wood is still going to be the thing that fails. So, and that's generally the case, right? As you saw in the lab when we did the knife test, if you looked at the composites lab, yeah, I think you have. Then hopefully you have. Then that's what we want, right? So we passed the knife test in the lab. Okay, so there are a number of different cure mechanisms. I'm going to cover 3 here that are the major ones. There are others, right? But I'm going to cover the 3 major ones, and I'm going to put it on my pad. So here we're not talking just specifically about wood polymers. We're talking about adhesive polymers, adhesives made from polymers in general. In fact, I don't know of any adhesives that aren't made from polymers. There probably are some, but I don't know what they are. So the first one is polymerization. And this is what we just talked about a few minutes ago. With polymerization, what you do is you apply a thermoplastic and generally by undergoing a chemical reaction that usually involves heat for the wood polymers, but doesn't have to. Crazy glue, super glue, they're catalyzed by the surface you put it on. Right? But you go through some kind of reaction and you make a thermoset, and that locks it down. Right? So you have a polymer that can have, and it can have a low molecular weight, and then you undergo a chemical reaction, and it increases the molecular weight and goes from thermoplastic to a thermoset. Well, when you go from thermoplastic to thermoset, you increase the molecular weight, right? Because you're just making a bigger molecule. So polymerization is the first cure mechanism and the one that we use in wood adhesives. The second one is solvent loss. A good example here is paint or latex adhesives. Also, PVA, polyvinyl acrylate, which is white wood glue. So it's also, if you've used rubber cement where it smells when you apply it, or Duco cement, when you were a kid, if you made models of something and you glued them together, there were plastic models and you glued them together with plastic cement. Basically, you had the diffusion mechanism there. It was the mechanism that was forming the bond, and you had you also had solvent loss as the cure mechanism for that. Okay. So the third one is hot melts. So here you just have a polymer that has a low enough molecular weight. It's still high, but it's low enough that when you melt it, it's reasonably fluid. So then you can apply it as a fluid, and as it cools, it becomes a solid. So that works fine. It is a mechanism. It does work. The reason you don't use hot melts for everything is because the molecular weight has to be low enough that it will melt in the glue gun, and for that to happen, the molecular weight is low enough that you don't have a high enough molecular weight to get really strong bonding. Well, really strong cohesive forces is what I should say. So you have the higher the molecular weight in general, the stronger the fracture strength of the polymer on a bulk basis. Okay. All right. Now we can go back to this and this, this. Come on. There. So now you've learned the fundamentals of adhesion and polymers and how they work as adhesives and the different cure mechanisms, at least some of the different cure mechanisms. There are others. So, I mean, adhesion could be, there are scientists that spend their entire careers working on adhesion. In fact, there's a bunch down at in Eugene at Hexion and the other glue manufacturers around, GP and Albany. So you have, what we're gonna do now is, we've talked about the fundamentals of how it all works. Now let's walk through how you actually form an adhesive bond. So the first and most important step is surface prep. I've said it before, if you have a dirty surface, you'll do a great job of gluing the dirt and a poor job of gluing the substrate. So you apply the sand, so then you have application. And there's more to the surface prep too, and in the next slide is with wood. Wood has some special considerations about surface prep, and we'll talk about those in another slide. So you have application, and the thing here to remember is that generally you only apply the glue to one substrate, okay? So you apply it to one, for example, plywood. You put the glue on one piece of wood. You saw this in the lab, LVL, same way. Put the glue on one piece of wood, and then you put a piece of wood on top of it that doesn't have any glue. So what happens then is the glue has to transfer, and it has to wet it has to wet both surfaces, but it has to wet the top surface also. And what we want from that is flow and penetration, right? So flow is very simply flow in the horizontal direction, because if it goes on as drops, as it does with particle board, MDF, and OSB, you get flow. You're going to have drops, and you want it to flow, especially as you close the press. You want it to flow, and you want it to penetrate. You don't want it to penetrate too much, but you need it for it to penetrate some, because that's where the mechanical interlock comes in, right? If you know the fundamentals, it all makes sense, and you can solve problems that otherwise you wouldn't be able to solve. So you have flow and penetration, and you wet both sides. You can kind of get some issues here. So if you're gluing the wood and it's hot, just came out of the dryer or whatever, and you put it on here and you end up with too much time between the application and the transfer step, then you can get a pour bond on this top piece that didn't have any glue to start with, right? So then you can get adhesive failure. So you need to do it right, and then you increase the pressure, and you've got heat going on here. So in general, for the major wood composites that are made in a mill that we're talking about, you have pressure and you have heat, and the heat triggers the reaction, the polymerization mechanism for the glue. And so you go from a liquid to a solid, and it's penetrated the wood substrate. So you've got mechanical interlock, you've got intimate contact, so you have van der Waals forces and hydrogen bonds, and you get a good adhesive bond that gives you cohesive failure of the adherent when you test it. So that's how the process works in glue and the different concepts involved. Now, some of the things that can happen with wood is you can have surface aging. So this is some experiments that were done. And so here you have whole wood, and here you have wood that's been extracted with a extract wood with a solvent, what happens is you remove the extractives. Right? So Douglas fir has extractives, right? And you can see that, and what you want here is a low contact angle. The low contact angle means the drop is flatter, means you have more spreading. What you really want is a contact angle of 0, because that's called spontaneous wetting. So you want the contact angle. So this is, you want the contact angle. This only goes to 30. You really want it to be 0. That's the best, but you hardly ever get that in practice. So the lower the contact angle, the better it is, because when you spray the drop on the particle board or the MDF or the OSB, then it spreads out. You want it to spread out. Okay. Redwood has fewer extractives, and you can see that so this is going up to 80, this is going up to 70, so it has a lower surface energy to start with, and doesn't have the extractives that Douglas fir has. But you can see with both of them, you have surface aging phenomenon where the contact angle increases with time. Now, it doesn't show it here, but it is actually the case that all you have to do to get a good, to reduce the contact angle back is just to sand the surface, because what's going on here is surface aging. It's not the entire piece of wood. So the key here, so when you're trying to glue wood, you want to get to get the best bond, you want to glue it as soon as possible after it's been machined. That's the main lesson here. Also, be aware of extractives, right? And there's another issue with extractives. So Doug Gardner, who's at the University of Maine, and Mike Wolcott's at Washington State, so Dave Gunnels, back in 2007, they did some really interesting experiments here. So you know what transesterification is? So this is what's going on. They believe that you have transesterification between the extractives and the wood substrate itself. So what they did was, before they extracted it, and these are hours of time after application, right? So, or hours when they measured the contact angle. So here they measured, and this is the contact angle over here. So when the wood was exposed to light and air, and I don't know what species this is, we have to go back and look at the paper. When they're exposed to light and air, you get this surface aging phenomenon very strongly. You go from 20 up to 70 something. Right? But if you keep the wood in light and vacuum, or dark and air, and dark and vacuum, so if you get rid of the light and you get rid of the air, you get very little surface aging. Right? Then they extracted it. And after they extracted it, it didn't matter, right? If you had it in light and air, dark and air, light and vacuum, dark and vacuum, it didn't matter. You didn't get the surface aging phenomenon. So clearly this demonstrates that the surface aging has to do with extraction. And the reason this is important is the extractives are generally hydrophobic. So if the extractives come to the surface, then you have a more hydrophobic surface, you get less flow and penetration when you apply the adhesives, and you get a weaker adhesive bond. So that's why this is important, right? So this is a really good set of experiments here. And it shows you that you need extractives, and you need light, and you need air to have this take place. So, and you're gonna have that in the mill. You can't run the mill in the dark, and you can't run the mill in a vacuum, right? And you can't extract the wood. So you need to be aware that this is a problem, and that you also need to be aware that if you're having trouble with gluing because something in your process requires that the wood be sit for a while after processing, before it gets glued, run it through the sander again. and then glue it, right? Okay. All right, so let's talk about specific polymers here.
First, I have a quick question.
Sure.
I just wanted to be very sure about what you meant by the contact angle. Is it the angle between the adhesive?
Right here.
So,
This theta is the contact angle. So you have a drop on the surface, and you have and you can draw a line that is tangent to the surface as it hits the solid, right? And then the angle between the surface and that line, that tangent line, is called theta, and that's the contact angle.
right.
And what you really want is theta to be 0. If theta is 0, this thing the drop spreads out until you're talking about nanometers, right? Thick. So you really want it to spread out. I can mention this too. If wood is very difficult to get a contact angle because the water soaks into the wood. So another way to look at not contact angle, but whether or not the wood has a high or a low contact angle, is to just take a drop of water and put it on the wood and time how long it takes for it to be absorbed. If it's absorbed slowly, then you have a more hydrophobic surface. If it absorbs quickly, you have a more hydrophilic surface. And so that'll give you a clue as to what's going to happen with the adhesive too.
So, sir, the viscosity of the adhesive actually plays a huge role in this, right?
Well, of course, viscosity enters into all of this, right? And one of the reasons that you use a hot press to kick off the reaction, but another side benefit of a hot press is you lower the viscosity. So you get more flow and penetration at higher temperatures than you do at low temperatures. But if you have adhesive like PMDI, the isocyanate-based adhesives, they have very low viscosity to start with. So that's because they really cross-link like crazy. So you can get a high molecular weight, you get very high reactivity with the isocyanates. So you can start with a low viscosity fluid, and you can end up with a really high, not high viscosity, but high molecular weight polymer. In fact, you have I always like to say that the largest molecule in the world now, I think, is a fungus or something that grows in Montana or Wyoming or something like that. But one of the largest synthetic polymers is the wing of an F-15 fighter jet, or any kind of fighter jet, right? Or even the Dreamliner. The Dreamliner is carbon fiber epoxy composites, and the epoxy is thermoset. So the Dreamliner airplane, Boeing Dreamliner airplane, that's one giant molecule, or the wing is. The wing is a molecule, the fuselage is a molecule. So, does that answer your question, Kenneth?
Yes, it does. Thank you, sir.
Okay. So now, so these are the advantages and limitations of urea formaldehyde. What I want to do now is go back to doing. So we have urea formaldehyde. So this is UF. So urea formaldehyde, on the screen here. Urea formaldehyde is this. So urea is, and again, the chemistry requirement for this class is high school chemistry. So I do not require you to memorize chemical reactions or chemical formula But there are some things in here I do want you to remember, and I will point those out. So formaldehyde is this. Okay, so the way these things cure, so these things use the polymerization cure mechanism, and the way they cure in 2 steps. So the first step is called methylylation. And this is okay, so you see what's happened here? You have CH2O, and the cis-C goes over to this nitrogen, right? So you have nitrogen here. The nitrogen is bonded to the carbon. I can write it like this too. Right? So you have one of the hydrogens on the urea, nitrogen, stays with the nitrogen. The other one moves over to the formaldehyde, and you have, and then you get this compound. So you have, naturally, because you have 4 hydrogens on the nitrogen, this can happen 4 different times. And this is another basic concept. Hopefully it's intuitively obvious. If you have polymer and they can only react at on 2 sites, you can only get a linear polymer. It has to react at more than 2 places on the monomer in order for it to cross-link and to give you a thermoset, right? So with urea formaldehyde, it can react 4 different places. So we're good. So that's methylylation. And then what happens is you have the second step is called condensation. So then you take another, so then you take a methylated, do it this way. And this will react. And what you're going to do now is you're going to lose water here. Right? So you're going to get this. Everybody see that okay? So the first step is methylylation, and the formaldehyde just adds to the urea. And this group here is called methylol group. So anytime you see that CH2OH, it's a methylol. You see it a lot if you look at a lignin structure, right? So that's the first step. The next step is condensation. Condensation because you lose water, right? So you lose water, and what you get here is a bond. And one of the things about urea formaldehyde is it can fairly easily, it can go in the other direction so that this is actually in equilibrium. And that's the main reason that you don't use UF in exterior applications. If it's too wet for a long enough period of time, especially at higher temperatures, it can undo itself and turn into lower molecular weights. You lose the adhesive bond strength. Okay, so that's UF. Next we have PF, which is phenol formaldehyde. Phenol is this compound. So that's phenol. See that okay? Plus the formaldehyde. If you remember your OChem, the oxygen here will direct to ortho-para positions. So
I'm sorry, Professor, could you say that word again? The oxygen does what?
it directs reactions. It activates the ortho and para positions on the ring. So this is, can you see this okay? So ortho is here next to, and para is across, right?
Oh, okay.
The
Thank you.
oxygen, right? So you'd hardly get any reaction at the meta. So you have ortho, meta, and para. Right? So typically you'll get a reaction here. And once again, the first step is methylylation. Okay. And the second step, you have now, there's a little bit of chemistry stuff going on here, because usually when we draw this, we omit the hydrogens, but in actuality, there are hydrogens here, right? So in real life, there are hydrogens there, but just for convenience, people don't draw them, because you're supposed to know that if you only have 1, 2, 3 bonds to carbon, something's wrong, right? So the fourth bond is hydrogen. So you usually don't draw the hydrogens. So now what you do is you lose water once again. So once again, we have condensation. So UF and PF have the same cure mechanism. Right? And I'm only drawing one of the reactions that can take place, because there are other reactions that can take place, and you can also have, again, you have ortho and para. So the phenol can react at 3 different places. So then now you can get thermoset, you can get cross-linking and thermoset. And the CH2 to the aromatic ring here is a more stable. Aromatic rings are more stable. They're lower energy. The carbon atoms are more stable. That's why lignin is more fire resistant than cellulose, and why phenol formaldehyde and resorcinol formaldehyde and stuff are more resistant to fire. So second step is condensation. And so then this can make, so you can then react at 3 different places on each ring, on each phenol ring, up to 3. It doesn't have to be 3. And the para is actually more reactive than the ortho. I'm not sure about that, but this is easier to draw, and it's what you see in the textbooks. So, and you also have water released. And the water is going to go off as steam, or it's going to, because you're above the boiling point when you press these things, 175C when we did the lab, right? Or it's going to soak into the wood and be absorbed by the wood, because you don't want to glue wet wood, right? If you try to glue wet wood, take wood that's above the fiber saturation point, and you put it in a hot press at 175C, it's going to explode. Right? You're going to make steam. And when you open the press, it's going to explode. And the same thing can happen with glues is if you have too much water or too much moisture, it'll be okay as long as you're under high pressure. But when you open it, you'll hear a pop and go pop. And that's called a blow. And it kind of looks like a blow because you'll get a bubble where you'll get a space where there used to be adhesive. Or you'll get a space between the adhesive and the wood. Okay, so that's PF, right?
Professor,
Yes.
I have a question. In the first reaction, which hydrogen is bound to form the hydroxyl group?
On urea?
No, in the top, the first reaction. More up.
But these hydrogens are the same. They don't care.
Okay.
Yeah. So this is formaldehyde symmetrical. So it doesn't matter which way it goes. It's going to look like this. Right? But in fact, these hydrogens stay with the carbon. Right? What happens is the hydrogen here is the one that goes goes here.
Oh yeah, that is my question. Okay, thank you.
Yeah. Okay. All right. So UF and PF are easy. The cure mechanism is the same. PMDI is different. So here you have isocyanates. And R equals an organic whatever. So it's chemistry notation again, commonly used in chemistry. You just use an R for to substitute for drawing a bunch of other stuff. Right? So we draw R, N double bond C, double bond O, and this group is called isocyanate. Isocyanate is highly reactive, and it can cause cancer if it's, especially if you breathe it. So you got to be careful about that. Today, most of the PMDI glues or isocyanate glues are manufactured in the when you get them from the manufacturer, they've already been polymerized to some extent. That's true for UF and PF also. Is they adjust the viscosity to give you proper flow and penetration for the specific wood that you're using, and the PMDI is the same. So it will be pre-reacted at the manufacturer's facility to give you the molecular weight, to give you the right kind of viscosity, to give you the good adhesive bond. So today, you don't have to worry too much about getting cancer from PMDI adhesives, but PMDI adhesives are still quite reactive, and you don't want to just, wash your hands in it or something. Okay, so what happens here is it still is two steps, right? So the first step, you have your isocyanate, and generally it reacts with water. And when this happens, you get this compound, and it is okay. But this reaction generally is fairly slow. Relatively slow compared to the second step, right? The second step is much faster than the first step. So you form this compound, but this compound has CO2 in it. And the CO2, this first step is slow, but then it will, this is not the second step in the cure mechanism, but the second step in this reaction. This hydrogen will come over to this nitrogen and the carbon dioxide will leave. So you get an amine plus CO2. And in the old days when they made polyurethane foam, they would typically just put in enough that they would blow it with the CO2 that's made internally. So the first step is carbon dioxide emission. This is what's generally true because in wood, so in wood you have lots of hydroxyls, right? And you can do this reaction with hydroxyls. So instead of H2O, you can react with this, with an alcohol, or with the hydroxys on wood. And then that's going to give you, again, this is going to flip here. Let's do it that way. And this is a urethane. Right? So that's how you make polyurethanes. Now these R's have to go on and continue to react, right? And generally when you have an isocyanate, this R, if we look at the spec sheet on a PMDI adhesive, you'll see that the isocyanate has usually between 2 and 3 isocyanates in the monomer or the repeat unit. So anyway, I'm getting off. Okay. The second step is also condensation. So what happens now is you've made the amine here plus, trying to go too fast. So amines react very rapidly with isocyanates, and if you take water or an alcohol and react with an isocyanate, you have to heat it and stir it and put in a catalyst to get it to go with any kind of reasonable speed. If you take an amine and react it with the isocyanate, it'll happen like instantly. And it gets hot, and its exothermic reaction reacts really fast. And you can put in different other modifiers for the reaction that can speed it up or slow it down. So there are different catalysts that you can use here so that you can tune the speed of this reaction. So this reaction is fast. Oh, and this is NHR, sorry. Oh, no, it isn't. No, it isn't. It's NH2. But it's still, this is still an amine, and it can still react with more isocyanates, and away you go. Okay. So, some of you may be using melamine urea formaldehyde. So, MUF. And melamine is this. And it's aromatic. Right. And some of you are also using, so it will react with the melamine is the similar to formaldehyde, right? Or I'm sorry, urea, right? So urea has NH2, C double bond O, NH2. So here you have the NH2, the amine group, and you have it on melamine instead of urea. And this will give you, actually gives you a stronger bond, a better bond, a more weather resistant bond, and also, but it's also colorless. And resorcinol is this compound. So you're also going to direct orthopara here. So this is going to be really reactive, and you're going to react all these different, at all the different sites on the benzene ring here, or the aromatic ring. And so you're doubly activated because you have another hydroxyl group. So it reacts faster, it cures at room temperature, and typically that can be used for CLT. But it's the same mechanism as before. You still need the formaldehyde. You still have methylylation and condensation. Right? So those are the cure mechanisms for the major food preservatives. And I went over time, and that concludes the adhesion section. Okay, so I think on Thursday, I think I can get through composites in the morning, and if you like, we can do wood plastic composites and nanocellulose in the afternoon, if you'd like to do that. And I'm going to attempt to send out a Qualtrics, and we'll see what people want to do. So I've been slow, and I'm usually slow, but with doing this remotely, I'm especially slow. I'm usually not this far behind, but I am now. So we'll see what people want to do. I don't want to make you be responsible for more material than is legally required, and so that'll be Thursday morning's lecture. And if you're interested and you want to hear about wood plastic composites and nanocellulose, we can talk about that in the afternoon. I'll keep it short, try and make it 1 hour, so it'd be a very brief overview, but hey, you'll have some familiarity with those two subjects. So you can expect some kind of a questionnaire from me. Maybe it'll just be an email with a yes and no. And that's what we'll do. And I appreciate your attention, and I've gone over time once again. So thank you for your attention. If you have any questions at all, let me know. The video, the recording for this lecture should go up on YouTube in a little while. It takes a little while for the system to process it. And so, okay. That's that. Any questions for today? Hearing none, I wish you all well. Hope you have a good Tuesday. And if I don't see you sooner, I'll see you on Thursday. So take care.
Thank you, Professor.
Bye-bye.
Professor.